Our guest today is Robert Pappalardo. His visit was made possible by the American Astronomical Society's Harlow-Shapley Visiting Lectureship Program, as well as the UNL Center for Science, Mathematics, and Computer Education. Bob did his undergrad work at Cornell and his PhD work at Arizona State, and after postdocs at Arizona State and Brown University, he was a faculty member at UC Boulder. Today, he's a research scientist senior research scientist at Caltech's Jet Propulsion Laboratory, where he has been for the last 8 years. His research focuses on the possibilities of oceans under the ice of Jovian moons, and he is designing a NASA probe to visit the moon Europa, entitled the Europa Clipper. His presentation today is entitled The Hidden Ocean of Europa, Exploring a Potentially Habitable World. Please welcome Robert Pappalardo.
Thank you so much. Thank you, Kevin, very much, and thank you all for being here. I've had a great visit, and looking forward to telling you a little bit about this guy, Europa. Those who came to the talk last night heard a little bit about Europa. You'll see a few of the same slides, but I'll talk more in depth about particular aspects of Europa, why we think it has an ocean, and what we think that means. And at the very end, we'll touch on the Europa Clipper mission concept as well, and I'll sprinkle that in along the way too. So this is Europa, moon of Jupiter. It's about the size of Earth's moon. Very bizarre surface, one that has very few impact craters, right? So it doesn't look much like our moon, though there are a couple here. There's one. Have stepped back to try to find another. Right? That's the only one in this part of the image. Based on the number or the paucity of impact craters, we think the surface age of Europa is about 40 to 90 million years old, something like that. We can count up large-sized craters. We know how often 10-kilometer craters should form on Europa. Count them up and we can get that surface age roughly. Though we don't have full coverage of the surface, we can extrapolate over the rest of the surface. Most of what we know is from the Galileo spacecraft, which orbited Jupiter from 1995 to around 2003, and it made about a dozen flybys of Europa. Only 3 of them were planned in the original mission, and Europa turned out to be so fantastic that the mission was extended and it was able to make additional flybys of Europa. So why do we care so much about Europa? Because we think it might have the ingredients necessary for life, and that's what we want to pursue in a future mission. And by ingredients, I mean liquid water, solvent, essential elements, things like carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, that would be needed to build organic molecules. This one's sort of a gimme because asteroids and comets bring that stuff into planetary surfaces. A harder one is chemical energy. We'll touch on that in a second here, but essentially the chemical disequilibrium that life would need in order for metabolism to occur. For metabolism to occur, what is really needed is a chemical battery, chemical disequilibrium. So could Europa have oxidants and reductants in its ocean that life might be able, such that life might be able to take hold? And then a stable environment. We'll touch on that just a little bit in this talk. But overall, Europa being a relatively large satellite, again, size of Earth's moon, and being in a tidal resonance, we'll talk about that just a little bit, we think, we're confident that Europa is currently at least heated by tidal heating, by this tidal resonance, by its orbit around Jupiter. By being squeezed as it orbits around Jupiter. And that tidal resonance, at least today, seems relatively stable. And so we expect that ocean to persist over time, though potentially the ice shell gets a little thicker and thinner. So I want to hit on this issue of chemical energy up front for the non-biologists in the crowd, and what we mean. Why it seems like if you have these ingredients for life, we might be able to get life at Europa. You know, we're used to what we do, aerobic respiration, take sugars and add oxygen and breathe out CO2 and water vapor. But there are lots of other reactions that can power life. Of course, photosynthesis, carbon dioxide, water, sugars, oxygen. But there are a bunch of others. These are just samples of more extreme kinds of life and the chemical reactions that occur in their metabolism. Iron oxidation is one, iron and oxygen and hydrogen. Methanogenesis, creating methane from CO2 and H2. There's a scientist at JPL who, when he first came to JPL, he said, is there evidence for CO2 at Europa? I said, yeah, there is some spectral evidence for CO2 at Europa. He said, then there's life. Because he's aware that CO2 and hydrogen can get together and make methane and water. So there may be the chemical energy that is needed. Now, we don't know that there's a lot of hydrogen around. We'll get to that. And there's sulfur reduction or oxidation. Just examples of the kinds of chemical reactions that we know on Earth can power life. We're familiar with these guys, but there are also lots of these guys. So it's chemosynthesis we're talking about, chemical reactions that can power life in the absence of sunlight. And some of the history here is we were getting our first glimpses of Europa from the Voyager spacecraft that flew by Jupiter in 1979, the twin Voyager spacecraft. Neither went very close to Europa. Voyager 2 saw Europa at 2 kilometers per pixel and gave us just a broad brush view. This is a Galileo map, but there's some Voyager data in here, but it gives you an idea of the resolution that Voyager had. It saw a bunch of lines and not that many large craters. And there were some hints of an ocean from Voyager data where in this region it was realized that some features had pulled apart as if on something mobile. We'll take a look at those areas close up in a little bit. And at the same time, people were doing calculations of the amount of tidal heat in Europa and saying, you know, it's possible that Europa might have an ocean beneath its icy surface today from this heat source. At the same time on Earth, we were discovering the black smokers, areas where they're pretty isolated on the ocean floor, yet teeming with life that feeds off the chemical energy that comes out of these black smokers, places where water interacts with rock, gets charged with chemical nutrients, and pours out of the ocean floors where there are tube worms, giant crabs, and things like that. So Europa and extreme life on Earth have kind of grown up together as fields and makes us think that it's not so crazy that a place like Europa might have life down there. So I'm a geologist by training. We'll hit on the geology a bit and the implications for an ocean. Europa has 2 main terrain types. There's the bright ridged plains, and then there's the darker mottled terrain. This is what the bright ridged plains looks like close up, crisscrossed by ridges and grooves, probably many generations of them. These double ridges are very common, even though we don't really understand very well how they form. They're both dark and bright bands. And then that mottled terrain, or chaotic terrain, where it looks like the older ridge surface has broken up, crumbled in place, and been replaced by this darker mottled hamburger-like terrain. I said there are not many craters, but you can see a couple here. A lot of the smaller craters on Europa are actually secondary craters. So a big crater like Quill here, or Pwll if you're Welsh, shows rays emanating from it, and a lot of these smaller craters are right along those bright rays. So like there are bright rays from lunar craters, it's places where stuff has been tossed out and made secondary craters. But it's the large craters we can assume are probably primary craters related to the age of the surface. So what do we know about Europa as a whole? Well, we know its density is about 3. So that tells us it's really a rocky object. But when we look at it spectroscopically, we see an icy surface and some non-ice material as well. So it's at least coated with ice, but it's mostly a rocky body. From gravity data from the Galileo spacecraft, we can estimate how thick that rock layer is. So the gravity data gives us an axial moment of inertia from Doppler. That is, the spacecraft is tracked and it's flying through a non-spherical gravity field. And from the measurement of the Doppler signal, the acceleration, deceleration of the spacecraft, we can start to get a measure of that gravity field. And so we know that from the axial moment of inertia, which is derived from that, 0.4 is a homogeneous object. So a smaller moment of inertia is more centrally condensed. Maybe you remember that from your physics classes. And so we know Europa has a central condensation, probably a small iron core, a rocky mantle, and then an H2O layer. So Europa seems to differentiate layered. And based on what your favorite rock density is, people try to pick rock densities based on the density of Io for a good ballpark number, Europa's neighbor. Then from various, then we can plot it as a function of the core radius compared to Europa's radius for either a pure iron core, or in this case an FES iron core. And this area of this diagram is showing the possible solutions for a three-layered Europa, where these contours are showing the possible ice shell thickness, H2O thickness. So the nominal number for the range of Europa's possible ice shell thickness is about 80 to 170 kilometers based on the gravity data. So typically I'll quote, well, about 100 kilometers for Europa's ice shell. But the uncertainty is certainly large. But I'm saying ice shell, but really I mean H2O, because gravity data can't tell us how much is solid ice versus how much is liquid. For that, we'll turn to geology. But the geology, as we'll get to, is only indirect evidence there's an ocean down there. As I mentioned last night, it's the magnetic field data that really convinces most planetary scientists that there's probably an ocean down there. Europa is orbiting around through Jupiter's very powerful magnetic field. If you could see Jupiter's magnetosphere in the sky, it would be bigger than the full moon in diameter. And Jupiter's magnetic field is tilted about 10 degrees compared to its rotation axis. And let me show you in this diagram. It's a complicated diagram, but it's fun, I hope worth it. So Europa's orbiting in the red plane here along Jupiter's equatorial plane. And there's Jupiter with minimal tilt to the orbit plane, just a few degrees. But the magnetic field of Jupiter is tilted about 10 degrees. So here's the magnetic equator of Jupiter for any given time. Now, Jupiter's rotating around once every 10 hours, and so therefore, so is the magnetic field. And Europa is rotating around, or orbiting around, sorry, in 85 hours, 3.5 Earth days. It takes much longer. So here's the fun when we get to watch the movie go. So you're Europa, and you're minding your business orbiting around, and you find yourself alternatingly below and above the magnetic equator of Jupiter. It's just going round and around the equatorial plane, but because that magnetic field of Jupiter is tilted, Europa is finding itself above and then below the magnetic equator. So and the yellow line is the magnetic field line connected to Europa. So Europa is feeling Jupiter's field vary, pointing inward, pointing outward, on half of the synodic period of Jupiter with respect to Europa. So the synodic period is about 11 hours. So about every 5.5 hours, the magnetic field flips from the perspective of Europa. And this movie's about to loop and have a little discontinuity. As soon as it does, here we go. So here's the magnetic field line connected to Europa, and that's showing that variation. It's flopping inward and outward. And so what the Galileo spacecraft's magnetometer observed is that Europa is generating its own magnetic field, an induced magnetic field, to counter Jupiter's field. There are eddy currents set up inside of Europa, and Europa is producing an induced field to counter Jupiter's varying external field.
How big is the field?
Jupiter's or the induced field?
Either.
I'm not sure if I know the numbers, so maybe it doesn't matter. Let me see if I can remember the answer. I believe it is maybe 10 nanoteslas, the induced field I'm talking about. It's small. I can check the right number, but it's something in that order, because for the mission, for the Europa mission, we're trying to measure the induced field to, oh no, it's less than that. I think it's less than that. We're trying to measure it to 0.1 nanotesla. And so I think it's only maybe 1 or 2 nanoteslas. It's small. Jupiter's much bigger. I'd have to look it up. So we're trying to measure this small effect. Oh, maybe it says here in this plot, does it? Is this? Yes, nanoteslas. Okay, so there we go. Oh no, it's more than I thought. Maybe it is 10 or 20 after all. Okay. So this gives you some idea of the amplitude. So it is more than 10 or 20 nanoteslas.
Is that the total, or just Europa, or just?
That is, yeah, so that's the problem, right? So that's what I have to check. Let me see if I can walk through this. This is the dash curve is assuming no induction. The ocean induction model is the dark curve. The observed is the red. Can't remember what the green is, sorry. Oh, that's right. They have various ocean induction models here, trying to fit the observed. So if you saw the curve with Europa out of phase, right? There's another curve where Europa is on the other side of the magnetic equator that's essentially out of phase with that curve. So this is the Europa component. And I believe it is here, 10 to 20 nanoteslas. So that's what Galileo was able to measure. With the future mission, so that tells, sorry, let me back up. So that tells us there's a conductor within Europa's surface, and it can give us some measure of the depth of that conductor. And it says it's relatively shallow, tens of kilometers. So what can be conductive within Europa in just the upper tens of kilometers? And so the conclusion is salty water. What this can't tell us is it can't separate the depth of that ocean from the salinity of that ocean, right? It's a product of the thickness and salinity. If we can measure this at a couple of different frequencies, then we might be able to separate out that depth and the salinity of the ocean. So future mission has the goal of measuring the induction signal, not just at the synodic period of Jupiter's rotation, but also at the orbital period, Europa's orbital period. And we might be able to tease out the separate thickness and salinity of the ocean. And that's where I bet the few nanoteslas comes in. That's probably the magnitude of the induction signal expected at Europa's orbital frequency. So, more than you want to know, probably about. Yeah.
So you said the revolution period is 2 hours?
85 hours for Europa.
So why does it change on the time scale of 30 minutes?
Oh, because it's Jupiter's rotation is 10 hours.
Yeah, so should that be the period then?
So yes, so here the period, yes, is 11.1. It's the synodic period
It looks like
of
it's
Jupiter.
just 20 minutes.
I'd have to check. I mean, no, it's definitely the frequency that matters, but the signal. Oh, because we're flying by Europa. So what the Galileo spacecraft is able to measure is just the magnetic field in the vicinity of Europa as it flies by, and then you have to understand where Europa was when this measurement was taken, essentially at a moment in time. And so we're talking about a mission. Originally, we wanted an orbiter of Europa. Now we're talking about a mission that will be also making many flybys because it's less expensive, and that's what NASA can afford to do. And so we've got to put together the story of 2 frequencies from flybys, which is going to be a challenge. But that's why we're doing something like 45 flybys, or it's part of why. So that's part of the story of why we think there's an ocean, but tidal heating is part of the story as well. So here's a little bit of what Europa's doing as it orbits around Jupiter. So this is not to scale, but Europa has an eccentric orbit, an orbit that stays non-circular because Europa is in a tidal resonance with its neighbors, Io on one side and Ganymede on the other. And the push and pull from Io and Ganymede in this resonance means Europa is not able to circularize its orbit. And generally, satellites will circularize their orbit over time. But because Europa's orbit is staying eccentric, what happens is as Europa is closest to Jupiter, at perigeo, it is stretched out a bit. And when Europa is farthest from Jupiter, it contracts a bit. And it also is librating as it orbits around Jupiter, such that its tidal bulge is facing toward Jupiter. So Europa is orbiting around, has a radial tide, and has a librational tide where its tidal bulge is essentially sloshing back and forth. Both of these contribute to the heating of Europa as Europa is stretched around and deformed as it orbits around Jupiter. If Europa has, and that's at the 85-hour orbital period, if Europa has an ocean, then that tidal bulge is predicted to be about 30 meters in amplitude. If there's no ocean and the ice is instead coupled to a rocky mantle, then it should raise and lower only about 1 meter. So if we can measure that directly, say from a laser altimeter, then we would know for sure that Europa really does have an ocean. But as we'll talk about, there's a lot of indirect evidence that it does. The fact, well, let's see. I'm going to skip over this a little bit just in the interest of time. We'll come back to this idea of nonsynchronous rotation in a minute. So, not to scale again, but it shows you, this illustration shows you the idea of Europa kind of breathing, if you like, moving in and out its tidal bulge, stretching and contracting as it orbits around Jupiter. An important concept here is that where the interior of Europa is softest, or closest to the Maxwell time for the physicists in the crowd who know the concept of that place right between elasticity and viscosity, that is where the ice, that is where tidal heating will concentrate most. So the surface of Europa is about 100 Kelvin, very brittle. It's not deforming viscously at all. But the base of the ice shell is as warm as glacial ice, right? It's the base of the ice shell. It's going to be near 0 degrees Celsius, about like glacial ice on Earth. And so that part can deform viscously. And so that is where heating will deposit the most. So Europa is like a paperclip that's being bent back and forth and generating frictional heat as related to this tidal heating. We don't know whether tidal heat is deposited into the rocky mantle of Europa because it depends on how stiff, cold, or warm that mantle is to begin with. If it's cold and stiff down here, like Earth's moon, then there's not going to be much tidal heating because it's too stiff to deform significantly. But if it's warm down here, then it'll stay warm and actually could heat up even more because it is deformable and tidal heat can deposit down there. So we don't really know if there's tidal heat deposited in the rocky mantle, but there should be lots of tidal heat deposited in the base of the ice shell, wherever it's softest. In fact, you could have runaways where if there's a little spot of warm ice that rises up to the surface, well, that warm ice will be tidally heated even more and might thermally run away and melt. Let's talk about some of Europa's specific landforms. I mentioned ridges here we are at, oh, I don't have a scale mark, but these dark spots you see are generally about 0.7 or so kilometers across. These ridges are typically a couple of 2 to 5 or so kilometers across. So these ridges crisscrossing everywhere on Europa's surface. Many of them are in sets of ridges. Some have very bizarre shapes and cusps, like this guy here that we'll talk about in a minute, or this one here. These are called cycloidal features, a cycloid being the absolute value of sine of x, something you wouldn't expect to see on a planetary surface, but there it is, and it took quite a while for a good hypothesis to come about as to how they formed. We'll talk about the stresses affecting the surface a little bit. So Europa is going around its eccentric orbit, stretching, vibrating, radial tide, vibrational tide. Here, this plot is showing Europa's surface and the principal stresses that affect the surface at one point in its orbit. Here is perigeo, which we'll call 0 degrees, closest point relative to Jupiter. So at the place facing toward 0 degrees longitude and away from Jupiter, Europa is being stretched out, so those areas go into tension in both principal stress directions. Europa is being stretched out. So you get tension toward and away from Jupiter because of that tide, and compression 90 degrees from that. And we can put this now into motion and look at the stresses for all points in Europa's orbit in a little stress movie here. There it goes. So as Europa orbits around, and where it is in its orbit is indicated here from 0, perigeo 1 to 80, apogeo and back around, you can see that the stresses are migrating across the surface of Europa. And in the equatorial regions, they shrink, become compressive, then go to tension, grow again, shrink, go back to compressive cyclically over 85 hours. And if you look either up in the north or down here in the south, where I can point more easily, the stress vectors are actually rotating around. So it goes from tension in one direction to compression, and that rotates around, becomes tension, and rotates around, becomes compression. Just a bizarre place for the geologists in the crowd to think about if you're worried about how fractures form on Europa's surface. And so it was realized that as this could explain those cycloidal features, potentially. Imagine a fracture propagating across Europa's surface, perpendicular to the greatest tensile stress, pull the surface apart. Well, that fracture, as it propagates, it's actually going to curve around to try to follow the greatest tension. And then compression is going to come along, and that fracture is going to arrest. And then in the next tidal cycle, that fracture may propagate again to form another curved feature. So let me show you this illustration. Here are some of those cycloidal features. Now these are ridges, not fractures. So the assumption is they start as fractures and then somehow become ridges. This is an example rotating stress tick down in the southern hemisphere there, where red is tension and blue is compression. And this is a model by Greg Hoppe from back in '99, who with Randy Tufts realized that if a fracture propagates and follows that rotating tensile stress, it's going to trace out a curved path across Europa's surface with each arc formed in one Europa orbit. So if that's true, that's a remarkable conclusion. It would suggest that lots of fractures form pretty quickly on Europa, that those fractures somehow then evolve into ridges. And it says that the stresses from this diurnal motion, because Europa's orbital period is the same as its day. It's facing the same face mostly toward its parent planet, just like our moon, one of its orbits around the Earth is its day. So that would mean that the stress from this diurnal stressing is great enough to fracture the surface of Europa. It's only 50 kilopascals is the prediction. That's a very small number. The strength of solid ice is something like 2 megapascals. So that tells us that the surface of Europa must be really weak if this diurnal stressing is really breaking the surface and forming these cycloidal features. And if there were no ocean, that amplitude would drop much further. So that argues that there is an ocean to at least get the stress up to 50 kilopascals.
Is the fracturing still going on?
So this would argue, I don't know. This has been used to argue yes, but what if, as we'll see later, Europa goes through cycles of having a thinner or thicker ice shell, or its eccentricity changes through time. Maybe this happened back when Europa had a higher eccentricity. Though with a surface age of 60 million years, that means there must have been change recently. But that's possible, as we'll see. So we don't know. My gut tells me that, again, we'll see why a little later, is that Europa went through a period of extreme activity and is now mostly quiescent and will again go through a period of extreme activity at some other time. We haven't seen direct evidence for changes on the surface, but we don't have the resolution and the temporal baseline to check that yet. We will with a future mission, I hope. Let's see, I'm going to have to hurry along a little bit, so I'll just touch on this. If possible, I'll just touch on this. Europa has global scale lineaments all over the surface, and one can see if those fit the diurnal stress pattern. The cycloidal features, yeah, they seem to fit, but what about the large scale lineaments on the surface? The best fit for them, or at least 40% of them, is this idea of nonsynchronous rotation of Europa. The idea that Europa's ice shell may slowly migrate relative to a tidally locked interior. If the ice shell is floating, then there's an extra torque, which I didn't take the time to point out on the other diagram, an extra torque which tends to speed up the rotation of Europa just slightly with each orbit around Jupiter. And so at least it's possible that the ice shell is rotating compared to the interior, which would be tidally locked compared to Jupiter. And if this occurs, we're talking a very long period, something like 10 to the 7th years for one non-synchronous rotation of Europa's ice shell. That can build up large stresses. And here's the stress pattern predicted from non-synchronous rotation. And take my word for it, when you do the statistics, these lineaments, or at least 40% of them, fit this pattern very well, being perpendicular to the largest red tick marks, to the tension direction. Other stresses that have been suggested are true polar wander. That is, the whole ice shell might flip over. It's coldest at the poles. The ice shell is expected to be thickest there. And so Europa can occasionally flip over, as been proposed for the Earth. But here it may occur regularly, where Europa's shell flips over because the ice shell at the pole is thickest, that wants to go to the equator, and then it thickens up at the poles again and thins at the equator, and it can flip over again. So some of Europa's features point to true polar wander as having occurred in its past. Really, what the bottom line here is we want to be able to tease apart this fascinating history recorded in Europa's ice shell, but we only have about 10 or 15% of the surface covered at good enough resolution to do that kind of mapping, to put together that kind of stratigraphy, the pick-up sticks kind of stratigraphy of Europa. And ultimately, when we have much more of it mapped, we can do much better. I showed this movie last night, zooming into one of Europa's double ridges. And these very common landforms, we don't know if they form the same way all these ones in the background did. This is a couple of kilometers across, a double ridge with an axial trough in between. The sunlight's coming from the right here, that's a shadow. It looks like pre-existing features might be bent upward somewhat, supporting an idea that something has pushed the surface upward. Here are some little blocks that have rolled down, some mass wasting down the sides of these ridges. This dark stuff seems to concentrate right along the ridges. Sometimes you hear the term triple band because the center is bright and then there are these two dark stripes on either side. Well, that one's a shadow, but there's dark bits up there too. Here are a few models for how these things might form. It's been suggested that maybe cracks go all the way down liquid water and there's volcanism that forms these linear ridges. It may be this tidal stressing squeezes out slush onto the surface. Maybe warm ice is pushing its way up like a tree root beneath the sidewalk and pushing up either side, the elastic layer, to form these ridge flanks. Maybe compression's involved. There's a recent paper that shows evidence that ridges are the sites of so some ridges we can reconstruct the features around, and so we can get a measure of whether it's been pushed together or pulled apart to form the ridge, and there are examples of both. And then it's been suggested that maybe water-filled dikes have come up from the ocean 9/10 of the way and pushed the surface up above them. The model I like the best, though, is one that says that there's a crack, say formed from diurnal stressing or nonsynchronous stressing or some combination or polar water. And that crack just goes through the brittle layer down to the warm ductile layer. And that diurnal tidal stressing, remember the stresses were going round and round. So what that does is if there's a fracture, that fracture will offset first one way and then the other way during Europa's day, during its orbital cycle. There can actually be back and forth strike slip motion along these fractures. And that creates heat, right? My hands are getting warmer as I do this, rub them together. So if there's offset of something like tens of centimeters, there can be enough heat, enough frictional heat along fractures on Europa to actually melt material along the axis and warm the ice to either side. That warmed ice would rise up buoyantly and push the surface up into a ridge, where it forms a plane of weakness that allows for compression to form a ridge. So maybe we're getting at plausible ways to form the ridges where shear heating is involved. We see very similar ridges on Enceladus and larger scale ones on Neptune's moon Triton, so it might be a common process. But then, one more, there's the LA model for how ridges form. It reminds me of my commute. It makes me feel uncomfortable just looking at it. We'll get to the McDonald's later, the little lenticulate. But this is showing a problem, because then and the rest of the image is real. We still have to understand how sets of these things formed, as if there's a whole shear zone or zone of weakness where lots of these ridges form. There's still a lot to understand here. Bands are fun, especially for the geological community who knows mid-ocean ridges and the topography associated with mid-ocean rift zones along mid-ocean ridges. So this is an example of a dark band on Europa. It was that area I pointed to early on and said from Voyager we had some idea that features were pulling apart. This one's called Yelland Linea. And in Photoshop, what you can do is cut out that band and push the surroundings back together, and it fits together perfectly without any gaps or overlap. And that suggests that the lithosphere, the icy lithosphere, the brittle layer, has been sliced right through and pulled apart. And we look at these things close up, so that area was investigated by Galileo, the Galileo imaging more closely, and that's what's shown here, those two frames. And you can see that there are lots of striations here in that dark band. So here's one edge of it, and the other is just up here somewhere in the corner. If you look at the nature of these things, a little tough to tell with the lights here, but there's a trough going right down the center of this thing, which looks a little different than all those other striations. a lot of these dark bands have a distinctive trough down the center. This one has lots and lots of striations on either side as well. Some just show the central trough and are nice and smooth, or a little bit of hummocks on the outside of it. So the fact that these can be reconstructed, there's a central trough down here, there's actually some hummocky material either side, and then we see these ridges and troughs to either side of that, is consistent with a spreading-like model, not too unlike what happens at terrestrial mid-ocean ridge zones. That there is a spreading center, there's a neovolcanic zone, that is an area where it's too weak and thin to support normal faults, and then normal faults form outside of that as stretching occurs. And then they stop. They don't get broader than about 18 or 20 kilometers. There was an abstract in a recent planetary conference that suggests the idea of some sort of subduction elsewhere on Europa. I should start adding that into my talk here. I don't have it yet. The paper's not published. It's just out as an abstract, where the suggestion is there might be underplating of elastic lithosphere below other elastic lithosphere on Europa. Because the obvious question is, well, okay, there's all this spreading, you see, what about the contraction? Here's an example of a little bit of contraction. It's not going to take care of all the extension, but this is the Astapalea linea region of Europa. This is what those images look like of this grayish band here. And if you squinted it, you can maybe convince yourself there are some undulations here. And this is a filtered version of that image that much more clearly shows the long wavelengths undulations. A big syncline here, a big anticline here, or I should say a trough here, and a bulge here, another trough, another bulge, trough, bulge. And when we look even more carefully there, maybe you'll be able to see that on this broad trough, in here, are these little crenulations. And on this broad ridge here are some little fractures, consistent with this being a long wavelength fold, where on the crest of the fold there are fractures, and down in the depressions, the synclines, there are little crenulations. So there's some minor evidence for folding on Europa, but not much. If this idea of underplating holds up, that would be exciting for understanding how Europa works. I've got to move. I'm running out of time here. Let's see. Impact structures, I'll just touch on them and say these largest ones are places where we think impacts have penetrated all the way through the ice shelf to create this bullseye-like pattern that went all the way down to a fluid layer, and then the brittle lithosphere flowed to try to fill in that hole and created those fractures. And that's a measure of the ice shell thickness. There are only 2 of these on Europa, and they suggest penetration through an ice shell about 20 kilometers thick. As far as composition, let me skip that one and go. No, okay, let's touch on this one. This is an example of a dark spot on Europa. There's some non-ice material that is staining Europa's surface. We understand a bit about it. This is the spectrum of icy material, like out here, and this is an example spectrum of that dark reddish material. It's just displaced here vertically for clarity. And that dark reddish material shows asymmetric, shallow absorptions in the near infrared. And there have been a suite of materials that have been suggested, but the best fits are hydrated sulfates such as epsomite, magnesium sulfate hydrate, and hydrated sulfuric acid. So Epsom salts versus battery acid are the 2 best fits. And it might be a little bit of each. It might be that sulfate salts have come out from Europa's interior whereas the sulfuric acid formed at Europa's surface due to irradiation from the Jupiter magnetosphere, hitting water ice and sulfur. Some sulfur might come from Io, and some sulfur might come from the interior, the MgSO4, and that may get processed into sulfuric acid at Europa's surface. Skip that one and go on to these guys. So these are these spots, the lenticulae, the dark spots that we saw a little bit before. Some of them have regular spacing. They're generally about 7 kilometers across. And we skip right to that one. And the idea here is that they represent convection of Europa's ice shell. So when ice gets to be about 15 or so kilometers thick, and if the bottom is warm and the top is cold, so Europa, we're talking 100 Kelvin at the surface, talking about 260 at the base of the salty ocean, with about 15 or 20 kilometers of ice above, then that warm ice is able to rise up buoyantly, and the ice shell should actually convect. This doesn't happen on Earth because we don't get packets of ice that are many kilometers thick. So Greenland and Antarctic ice don't convect, but on Europa, the ice is thick enough that it should convect. And this is a model by Ɂybys, who's now at Brown. The ice-ocean interface is here. The cold surface is here. And red is ice that's about 240 degrees Kelvin as it rises up and colder ice sinks down. It's more of a challenge to get these rising diapirs out of the interior of Europa. That would take either concentrated tidal heating in the rising columns before they cool off. Tidal heating just runs away and allows them to move up to the surface. Or perhaps they are cleaned of salts. And so if they're cleaned of lower melting temperature salts, they could just keep rising compositionally, buoyantly, because they're clean relative to their dirty surroundings. So those are a couple of ideas that have been suggested. And it takes about 10 to the 5th years for one of these plumes to rise up to the surface. Let's see, I'm gonna have to skip my movie. Another cool landform on Europa is this chaotic terrain, aptly named chaos, where blocks on the surface have rotated and translated in this kind of hummocky matrix, sort of like we saw before, but now there are these blocks that kind of look iceberg-like. And in looking at the smallest such blocks, which are about 1 kilometer across, in order for them to have moved, the viscosity of this stuff has to be less than warm ice would permit. It had to be at least a slushy water-ice mixture in order for the smallest blocks to have moved in this matrix. And an idea that was suggested recently, for a while it was quite a debate as to whether this is an area, these chaos regions are places where an ocean has literally melted up to the surface, or where diapiric ice has simply translated and moved these blocks around. But as I mentioned, warm ice alone seems to be too viscous. So a nice hybrid model has evolved in the last couple of years, where there's concentrated tidal heating within Europa's ice shell, melting in a zone related to such heating, and then collapse of the surface above a big subsurface lake. So an area like Thera Macula here, which is a chaos zone, may have formed above a lake the size of one of the Great Lakes on Earth. So it might be that in exploring Europa, we don't have to get through 20 kilometers of ice to find liquid water. It might be that there's liquid water at relatively shallow depths today below some of these chaos areas. And Schmidt et al. Who proposed this model suggests that based on the topography, this guy's low-lying there may be a lake under there today, whereas if the lake freezes up, it should push the surface upward, and you wouldn't see negative topography. So I mentioned the idea that Europa's evolution may change through time. So I want to touch on that before we end here. This is an example of one of those precious areas that where the Galileo resolution, the limited images from Galileo, are good enough to do geological mapping better than about 200 meters per pixel over this region. And Figueredo and Greeley have mapped this very carefully. And notice that these chaos regions, which are greenish here, are generally stratigraphically higher, more recent than the ridged surfaces. So it's not to say some ridges and grooves don't cut across the chaos, but for the most part, the chaotic terrains are younger. So that suggests that there's been a transition from formation of ridged plains on Europa to chaos over time. But the time we're talking about is just 60 million years, 1% of the age of Europa overall. So how could Europa's surface have gone through a change in the style of activity in just the last 1% of solar system history? And one can imagine we just happened to be unlucky and come along, and Europa has just gone through this change where it used to make ridges and had a very thin lithosphere, say, to a thicker lithosphere that started convecting. But that would be weird to happen to find that. Well, Europa's orbit is coupled to that of the other Galilean satellites, as I mentioned early on, Io and Ganymede. And some recent recent, now 10 years, by Hussman et al. Suggests that Io's evolution, shown in the dark curve here, varies. Its orbital parameters are predicted to vary as related to the heat flow of Io. That is, Io, right, is the most mechanically active body in the solar system, pours out heat, and there comes a time where Io can become so hot that melting goes on within Io. Well, tidal heating doesn't work in a melted body. In other words, it becomes too hot and therefore is no longer tidally heated as much as when it was a little bit colder than that. So Io can actually change its orbital parameters in response. So Io's eccentricity and semi-major axis are predicted to vary as related to the thermal evolution of the satellite. And so the dark curve is the prediction for Io, and because of the tidal resonance, Io pulls the other satellites along with it. So Europa is predicted to undergo changes in its eccentricity over time, with a period of something like 100 million years. And there are a lot of parameters to tune in this model. It's really just a proof of concept. But here they show a prediction for how Europa's ice shell may vary through time as related to its changing eccentricity based on Io pulling it around. So Europa may go through phases where the ice shell is so thin that it makes ridge plains and can't convect. And then its ice shell may thicken up to the point where convection kicks in. And then later it thins again. So we may just be coming off a cycle of a lot of activity at Europa, and we're in a waning portion of activity, which will pick up again. So that gets to the issue of, are cycloids active today? Well, maybe, maybe not. Maybe the ice shell is too thick today, and it's in a convective phase instead. So this is a summary of what I would argue is going on at Europa. We talked about it being differentiated with an iron core, rocky mantle, H2O layer, about 100 kilometers thick. About 20 kilometers of that is frozen. That leaves about 80 kilometers of ocean, which makes more than 2 times Earth's water volume altogether. Maybe there's hydrothermal activity at the base of that ice shell. We don't really know, but it's plausible. There are probably diapirs rising up through the ice shell, making domes and spots on its surface. Ridges, places where the ice shell is cracked and strike-slip motion is forming those ridges. Bands probably formed along planes of weakness that originated as ridges, and then the ice shell pulled apart, perhaps in response to nonsynchronous stresses. There are impact craters, a few of them. There are some that are so large that it implies that, and these multi-ring structures imply that the impacts penetrated right through the ice shell. There are chaos regions where it might be thermal runaways of tidal heating that have partially melted the surface of Europa. One more phenomenon at Europa was announced very recently. In December, it was announced that observations from the Hubble Space Telescope suggest water plumes at Europa. And really what was observed was glow of hydrogen and oxygen that correlated with each other. This is the hydrogen, the line alpha glow that was observed. They were seen over 5 orbits of Hubble, so it was always there in the same spot, although this contour is mapping the signal to noise value of 1. So this is not extremely robust, and it'll take confirmation future observations. In fact, this team has looked twice since and not seen it again. But the idea that there is hydrogen and oxygen concentrated at the limb of Europa in those observations suggests that there is a water plume or multiple plumes, and the H2O has been associated with H&O, and that's what we're seeing glowing in the ultraviolet. They might be transient. Maybe that's why we didn't see them since. They speculate they might be tied to Europa's tidal cycle. And at Enceladus, we know there are plumes, and recent work shows they definitely are tied to the tidal cycle. That is, they're most active at Enceladus in the south polar region when those fractures are held open by tidal stress, which occurs near the farthest point from Saturn, near Apoapus. And so the same thing might be going on at Europa. If there's activity near the South Pole, it may be when Europa is farthest from Jupiter in its orbit that they're most active. But we'll see, and time will tell with follow-up Hubble observations. If they are shown to be real, then, hey, Europa is currently geologically active, because we don't know that for sure. That would be great. And that Europa's native composition could be directly sampled from a spacecraft that flies through the plumes, which is what Cassini has done at Enceladus. I see it's 5, so if you need to give me the hook, I understand. Just a couple summary slides, if we have the time. So to look at those ingredients for life again. Europa, water, warm, salty ocean, twice Earth's volumes. Essential elements, accretion and impactors should bring that stuff. We see dark stuff on the surfaces of Ganymede and Callisto that's been brought in by comets and asteroids. They have ancient surfaces, though. Europa's dark stuff presumably has been recycled into its ocean, which is good. Radiation destroys organics in the upper tens of centimeters of ice. So if there were organics there, we wouldn't see them. So it's hard to know if they're there unless we go back and look at a fine scale at Europa's surface. As far as this issue of chemical energy, radiation of the surface creates near-surface oxidants. We see O2. We see evidence of peroxide and formaldehyde on the surface of Europa. So the oxidants are there. The question is, can they get into the subsurface ocean of Europa? What is that plumbing? We want to fly a radar to Europa, very long wavelength, which can penetrate through cold, clean ice and reflect off of water and show us the plumbing of Europa's ice shell. And then as far as the reductants, mantle contact means if there's a warm mantle and hydrothermal circulation, there could be lots of reductants in Europa's ocean. But even just serpentinization, just water contacting rock will produce some reductant, some hydrogen. So as long as there's continued cracking down there, there's a supply of reductants. As far as stable environment, overall, yes, though that activity level may fluctuate. It would be interesting to think about organisms trying to make it through the waning periods of Europa's activity. And then let me wrap up by putting this slide up, which summarizes where we are in this Europa Clipper mission concept. It would make 45 flybys of Europa. It's expensive to go into orbit around Europa like we originally wanted to do. It's about half the cost to be in orbit around Jupiter and make lots of flybys. This is what Galileo did somewhat, though with only a dozen flybys. It's what the Cassini mission has done at Titan with 100 flybys. We're really starting to understand Titan well. It would get objectives of the ocean, ice shell, composition, geology, and it would do reconnaissance for a future follow-up lander mission. This shows the model payload that we've been working with. These aren't the selected instruments, but just a proof of concept. Ice-penetrating radar, a stereo camera, infrared spectrometer, neutral mass spectrometer to sniff the atmosphere and any plume materials, gravity science, magnetometer Langmuir probes to try to get at dual frequency magnetometry, reconnaissance camera to get a ½ meter per pixel of the surface for a future lander, and a thermal imager to get at both thermal inertia on the surface and the search for any hot spots that might be there. Whoops, that's an old slide because it says 32. We're now looking at 45 flybys. And the cost estimate here is about $2 billion in FY15 dollars. And there's hope for this going through. NASA did announce with a budget announcement in early March that NASA will do a Europa mission sometime early to mid of next decade, in 2020s. They didn't say it would be this mission. They're looking to see whether there's anything lower cost still, but I'm hopeful that it will be a mission that looks something like this. So I'm going to stop there and take any questions. I appreciate it very much.
Questions for speaker?
Yeah.
You had some regions that were labeled as chaos. What does that exactly mean?
So the chaos is those areas where the blocks have moved around, rotated and translated.
Is there some phenomenon which you think is chaotic that causes this?
The idea is that maybe there's melting below this in the ice shell, and material above it collapses into that melted lands to form that chaotic terrain. So that's the working model, anyway. Yeah.
Some years ago, it was discovered that volcanic ridges under the Atlantic or Pacific Oceans are very fruitful environments for certain kinds of living organisms that feed on these noxious gases that come up from the center of the Earth. Here you have a water again, and you have something that's hot at the center. It would seem the only way to explore for life would be to drill down. Is that feasible with some remote robotic probe or something?
Well, the hope is, so you're talking about what might be going on down here, right? Hydrothermal activity. The hope is that if there is life down here, then there would be some signs of life through the ocean. Perhaps, life likes an interface. Perhaps there would be concentrations at the base of the ice shell where oxidants are flooding into the ocean. And this is speculation, I know, and then the hope is that convection might dredge that stuff up to the surface. So if that dark stuff that we see is really, at least in part, material from the ocean, then maybe life, if it's down there, could have made it all the way to the surface. Now, it'll be destroyed in the top 10 centimeters or so by radiation. So what it really means to search for life on Europa, as opposed to habitability, which our Clipper mission would get at. If you want to search for life, you've got to land on the surface and dig down at least 10 centimeters in that dark stuff to see what's in there. Oh, yeah. Not living today, maybe signs of life. So the hope is, if there are cells down there, maybe there are still cells here 10 centimeters or a meter down below the surface. But, first we've got to see, is there even evidence of any organics at the surface of Europa, or in plume material if we're lucky enough that the plumes are real, and then we can fly through those plumes with a capable instrument. Maybe if you can detect heavy organics, who knows? It was Freeman Dyson who said, if there's life at Europa, we should be looking for flying fish. meaning you know, by sniffing the atmosphere, we may be able to get at that. Yeah.
You said that the ice penetrating radar works, incredibly well on clean ice, even this ice this big. What about ice that has salt, the salt in it from the ocean?
So that's exactly right. So ice penetrating radar is okay with sulfates. It's not okay with chlorides. And another recent result that I didn't touch on here is that maybe magnesium chloride is the native ocean material that's coming up to the surface, because there is some chlorine observed in the very tenuous atmosphere of Europa. So a recent paper suggested magnesium chloride. Then radar is not going to penetrate deeply, and it'll just map out the brittle, cold surface layer, and it'll get cut off either when it makes it to chlorides or when it makes it to warm material. The hope is if the ice shell is convecting, there are also downwelling regions that are especially cold, actually even colder than a conductive profile. Maybe those will be windows to the interior. If chlorides are common, then we're going to have trouble with radar. Yeah. And we might just get a very shallow layer of Europa's subsurface. Other questions? Yeah.
If money were no object, what would you like to have on your Europa mission?
So I want to go into orbit, so we can do the gravity and altimetry and magnetometry right, because through flybys, that's tough. And I'd want to drop off a capable lander that could dig down and understand what that dark gunk is and whether there's evidence for organics there, which had probably a microscope and a mass spectrometer on it. That would be pretty incredible.
Have you been working with Ɂybys and his under ice floating rovers?
Oh, so I don't know him in particular, but there have been proposals for let's melt through the ice and then release a probe. But first we better understand how thick that ice is.
Right.
And melting through, and it's not going to be ice. There's going to be some magnesium sulfate salts melt at 100 degrees Kelvin higher temperature than H2O. So we might have to melt right through the salts. So it would be a challenge to do that. So that might happen 100 years in the future, but I doubt it's going to happen in a long time, unfortunately. Yeah.
So salty doesn't mean sodium chloride.
No, in this it could.
All kinds of salts.
Right, magnesium chloride is a possibility, but magnesium sulfate is definitely a possibility too. And again, we need better data. We're at the point where most of the discoveries have been, we're kind of like Mars was after Viking and before Pathfinder, really in need of more data to make leaps in our understanding of how this place works. All right, so I'll stop there. Please feel free to follow up.